Take three. This is a little lecture guide to the robotics week. I don't want to really go on a full lecture about this, but I probably will go off on tangents. This is take three, so I have to remember all the things I said in the other that I didn't actually say in this one, so I don't forget them. But there's no textbook. So that's the first thing I should say. At the current state of this class, there's no textbook chapter on robotics. We probably talked a little bit about it in earlier chapters when we talked about AI and stuff like that. But this fully robotics chapter is from the textbook, the former textbook of the class, which was the textbook when I first taught the class a little over a year ago. It was a textbook written by Dr. David Brown, who wrote this comic book. Basically, this is chapter whatever the comic. I think this might be chapter 10, but chapter 9 it looks like. Okay, yeah, 9 robotics. This is a chapter from that textbook, and I think it's good textbook. I'm not sure why the decision was made to change it. I wasn't involved in that. Probably because of the pandemic and the need for more sort of online interactive type stuff that you have with Cengage is the opinion on it. Frankly, I think the textbook is still fine. It's a little dated in places with the examples, but the fundamental concepts are still, I'm not going to say they're timeless, but they're, because this textbook does talk about fundamental concepts don't usually change very quickly. So even though the examples of robots might be more sophisticated now from when he first wrote this textbook, the concepts haven't changed. So it's I think it's a great textbook. I like it. It's a free resource too, so that's also nice. So our careers did not overlap at Pellissippi. He left shortly before I did. I feel like in a way he left one of the holes that I filled in when I was hired. But we did overlap. I think I spoke to him briefly at, I have to remember that. I haven't covered this yet in this take of the video. CodeStock, which is a conference in Knoxville for programmers. Typically .NET stuff, but like any programming topic could be covered here. But there's a lot of .NET people. I remember that being like the predominant people. So like C# coders and stuff. So he gave a presentation there more or less on this course you're in right now. That's my take on it, because he used to be the head person of this course, and he used to use a different textbook before he had the comic book, I think. I'm not sure about the timeline here, but I know at some point he used this textbook, which you might remember I mentioned Daniel Schiffman before. He had the robots in the artificial intelligence chapter that we covered with the robots that were trying to get to the goal. That is an example that was in turn inspired by this guy. My example's messed up already. Here we go. Here's the original paper by Craig Reynolds. A lot of stuff that Daniel Schiffman does. Again, Daniel Schiffman wrote this textbook, and Dr. Brown gave a presentation on using this textbook for his class, which I think was 1301, or the equivalent. It might be a different number back then. And The Nature of Code, it's a free book. You can get a print edition for like $20 or $30. I don't think it's necessary. I assigned it because of Dr. Brown's talk at CodeStock. I used it for it was a computer math course I was teaching, and we were kind of just until that time we were reviewing like fractions and stuff. It was like a general beginning college math or a college math review course before I changed it to this book, because this has a lot of math and physics in it, and the course description at the time, it was a different school, did talk about physics and other math. So I thought this was a great book, and it was like probably my favorite course. It went from my least favorite course to teach to my most favorite course to teach, because we got to do a lot of this. This book's about modeling nature in all kinds of ways, like visually. It's principally using the processing language. Processing is a wrapper on top of Java. So it's basically Java, but it's a way of like visually representing physics and stuff in the real world. And then you also saw the stuff about AI and that kind of thing. So I recommend this book. Again, it asks for a donation, but you don't have to make a donation. And you can just like go to Read Now here and read the book online. It has the whole book with interactive examples. If you go far enough, you can see. Yeah. So it's a really neat way of showing you how you can model lots of things like gravity and friction and stuff like that. Beautiful, beautiful book. And I also recommend Daniel Schiffman. He's a professor at the Tisch School of Art, which is part of NYU. So I want to say he's primarily a programmer, but he's involved with art. One of my best friend's husbands actually is a creative coder, and he's referenced in this book. His name's Robert Hodgin, and I have an example of his here too. I might have to pause to find it because I thought I had it up. Hold on. All right, before I show you that example, I'm going to show you because I have this pulled up. This is a simulation from 1986, which is before the year the book came out. This is like, you could tell it's old school graphics of Craig Reynolds' simulation of his Boids. He calls them Boids, which I guess is like birds that are androids, but also maybe like a New Jersey accent or something. I don't know, the Boids or whatever. It's some kind of play on words. But the reason why I'm talking about all there's a whole thread of interrelated stuff here, both personally, because I like, my friend's husband, and then there's Daniel Schiffman, and there's Dr. Brown. Oh, by the way, here's this Daniel Schiffman, by the way. It just sort of automatically went to video, but I recommend like watching his videos on this, where he shows, again, inspired by Craig Reynolds. So what's the thread here? Craig Reynolds is like, he came up with this idea of modeling this behavior, and Daniel Schiffman goes on about it quite a bit, this idea of desire. So this is getting to what robotics is, and we'll talk about the cybernetic loop here in a second, and that's when I want to highlight. You want to know the cybernetic loop. But you could just like, right, if you're a programmer, you could just say, okay, this bird goes this way, this one goes this way, this one goes this way. But instead, Craig Reynolds modeled this thing called desire. Like, you give these things, each one of these birds, a certain goal or desire, a thing they want to do. And there's some rules about it if you read the paper. For the flocking, what they want to do is they want to stay pretty much around the speed of the group. They want to follow other birds in the group, but they don't want to. But they also want to not collide with other birds or boids in the group. And then that gives a rise to this. A lot of this stuff has to do with emergent behavior. You set a bunch of rules down about what the things want to do. And again, desire is like this idea you're modeling. Is they don't really have desire, right? They're not actually alive, but you model this idea of desire. They have certain goals. You establish the rules for that, and you see what the emergent behavior is, which is kind of this. Let me silence this. You can look at it. This flocking behavior. This title is in the way, but you can see how they kind of like try to follow but not collide. And his simulation looks like they're colliding a little bit, but they're trying not to anyway. And so pause 1 minute. I'm already 8 minutes in, but I want to show you the example. This is a simple. I was saying this is a simple example, and then I paused the wrong thing. I paused the recording instead of the video. But that was a simple. I mean, simplistic looking. It's rudimentary. The graphics. Here's my friend's husband, Robert Hodgin is his name. He's got his degree in sculpting is what it was, but he learned programming and does a lot of creative coding. And this is one of the earliest things he got into was this flocking behavior and modeling it. But as you can see, it can be more artistic and more complex if you've got the machine that can handle it. This one's actually fairly simple compared to some of the other ones he's done, but this one's called Murmuration, I think. So you can kind of think of this as an art piece, but check out his other stuff if you want. It's on this page that I linked. You can go through this. You can find his other art. And again, Daniel Schiffman references Robert Hodgin in his book, where he talks about something called additive blending, which is a lighting technique in one of the chapters. But so there's just like this thread of relation that's kind of neat. I'm not going to say glitch in the matrix type stuff, but I just spent about 20 minutes probably talking about Isaac Asimov and the 3 laws of robotics and some stuff, and realized it wasn't recording. So anyway, I went on too long, honestly, about that stuff. So anyway, but let me get back on track. So I was just talking about murmuration, and the reason I was talking about murmuration, the flocking behavior stuff. And the reason why I brought that example up is because it's based on this Craig Reynolds stuff. And again, Craig Reynolds influenced Daniel Schiffman, influenced Robert Hodgin, and Daniel Schiffman also influenced the former professor here who wrote this comic book, who influenced in turn me. So I have several like avenues of connection, web of connection to these people, directly or indirectly. But the reason why I was talking about this in particular is because we're talking about robots this week, and Craig Reynolds, if you look through his stuff, he has this whole thing about desire. So I think I mentioned that, the desire to stay close to the flock and a desire to avoid collisions within the flock. Those are the two major goals of the cybernetic loop. So I don't think I talked about the cybernetic loop. I talked about this, and then I talked about the 3 laws of robotics. So I hope this is not a repeat, but here's the cybernetic loop. I know it's not Dr. Brown is like me. It looks like he likes etymology a little bit. So this is the Greek word kubernetes, which means kubernetes. It means steersman, governor, pilot, rudder. But that's where cybernetics comes from. So the cybernetic loop has to do with this thing right here. And gosh, I've already described. I hate repeating myself because you haven't heard it yet because it wasn't recorded, but then I hear myself repeating the things I said. It makes me self-conscious. But so the cybernetic loop has 2 main components, sort of. I mean, there's more than that, but there's the sensing and then taking action. So the cybernetic loop always has to do with a thing in the real world that has the ability to sense the real world and that has the ability to affect the real world in some way. So like the easiest thing to think about is like the robotic car, self-driving car, like a little robot toy or whatever that wants to get from point A to point B. So the starting place is point A. Point B is the goal. Let's say some spot 10 feet away. And the little robot has a way to move. So those are usually this is a term you need to know for tests and stuff. Servos or servo mechanisms. They sort of correspond to muscles in a way. Ways to affect or move in the world. Somebody just went for a walk and left the dog, so he's gonna whine. So the sensing could be anything that like tells the entity about the real world somehow. So in Lego Mindstorms is I didn't do this last time, so let me do it this time. Is an example that we cover a lot because we used to actually build these in class. This is an older model. Actually, we have the newer model. But so there's some questions about Lego Mindstorms in your quizzes and stuff. I'm going to pause for a second. Try to get the dog to calm down so I can make this video. I hate my life. All right. So Lego Mindstorms, we didn't use them in class, and so these are some test questions. This is why I'm showing this to you. So you got a light sensor. It tells you color and brightness and that sort of thing. So this is taking input from the outside world. So this could be used, for example, to solve a Rubik's Cube. There's a Lego Mindstorms robot that solves a Rubik's Cube. So that's not like the classical easy example is thinking of a robot moving, right, through space or something. But this is one where the robot that uses the servos to twist the cube sides, the sections, right? And then the light sensor looks at each square and then figures, but based on the programming, it will take an action to rotate the pieces of the cube to get closer to the goal of having them all the same. Solved Rubik's Cube. So that's one thing. You have one that can also sort colors that we actually built in class. We didn't have all the pieces, the servos we needed for the solver, but the Rubik's Cube solver. But we did have one that would sort pieces by color and move them on like a conveyor belt kind of thing. The ultrasonic sensor is like echolocation for bats. It's showed here in one of these slides. He's got a picture of a bat doing the echolocation. Here it is. That's what the ultrasonic does. So it's, ultrasonic means higher than human hearing. Above, beyond sound is what ultrasonic means, I think. Like ultraviolet is beyond the violet part of the spectrum, which is the high energy part. And infrared is below the red part. Infra means below. So there you go. Some etymology tips there. So below the visible red part and above the visible violet part. There are those two, ultraviolet. So ultrasonic would be things that are above what human frequencies higher than what humans can hear, which is typically what echolocation is with bats, little squeaks, right, that we can't hear, and they bounce back and they can tell where things are. And so ultrasonic's used for seeing how far you are away from an object if you're a robot. So this is all what I'm talking about is all the sensor stuff. And then the servo motors are the take action. So these are like typically like little motors that turn, that you have sticks and gears stuck into to turn wheels and that kind of thing. So that's just Lego Mindstorms robots, but any robots can have these things, right? So a self-driving car will have LiDAR. This is the laser ranging thing, or maybe GPS, other things like that to sense where it is in the environment. And then its goal is to get from city A to city B or whatever and stay on the road. That's another. So this goal can be multi-part, right? With like the example of the birds of Craig Shergold, they want to not collide with their neighbors, but also follow their neighbors as closely as possible. That's flocking in general. And that gives rise to emergent behavior. I said emergent behavior in one of the takes of this video. I don't know which one, so I'm repeating myself. I'm sorry, but you give these basic rules for a system and you see what behavior emerges from it. It's kind of hard to predict. You can do the rules. That's the easy part. As long as they're well defined, but then you see the emergent behavior, which is in that example we just saw before I realized I wasn't recording with Robert Hodgin and not swarming behavior. That's another behavior, but flocking behavior, like knowing how that shape will, change. It's kind of hard to predict when you got 500,000, I think, different birds in that particular simulation. So it's like kind of hard to predict what's going to happen, what waves of undulating stuff will happen. But it merges for those basic rules and from the cybernetic loop here. So you want to know this guy's name. Norbert Wiener is all it sounds like if you made up a name for a dork, right? That would be the name. I mean, Wiener means literally someone from Vienna or Wien in German, but Norbert, I mean, you couldn't pick a better nerd name. Anyway, he's the guy who came up with the cybernetic loop. So know his name. These are just things I'm pointing out that you need to know. You need to know the Mindstorms dude. What's his name? Actually, just because we covered it in class before. Let me give that to you here a second. But you make sure you know the cybernetic loop too in order. Just know this. We go back to that because we just covered it. I want to make sure you know it's sense, and then compare to goal, and then it's determine the action you need to take. And that's kind of like in between here. And then take that action, and then sense again to see if you're any closer to the goal. Once you get to the goal, of course you stop. You've achieved the goal. But like assess how close you are to the goal. Check to see if you got to the goal. It's kind of like a blur between those two, right? But and if you're not at the goal, then determine what action you need to take in order to get closer to the goal, and then take that action and then reassess with sensing in a loop over and over again. So sense, compare to goal, determine action, take action in a loop over and over again until you get to the goal. That's the cybernetic loop. Norbert Wiener is the guy who came, or Norbert Wiener. I don't know how you pronounce that. I don't know if he was German or not. He was at MIT, but whatever. He could have been born in Austria or Germany or Switzerland or something. But he's the guy who came up with cybernetics as a concept and that name. The Mindstorms guy for Legos named Seymour Papert, Papert. It's in here. Just remember that name. Just remember the Mindstorms guy. And again, I'm giving you answers to questions basically here. But you also need to know these other things, like what a servo is, what does it compare to. It's kind of like muscles. I think there was a question at some point about how these frame parts, like these actuators and motors and stuff, are kind of the servo mechanisms are kind of like comparable to muscles. And then the frame stuff. There's a picture in the Mindstorms of this. You can think of those as bones, sort of, but like these things that join things together. It's not really part of a robot, though, so I don't know why you would talk about bones in particular. They kind of go without saying, in my opinion. But the servos are the things that take actions, the motors and the gears and stuff. And then again, the sensors, you could have things that sense light and things that we can't even see, right? You could have them that sense Wi-Fi signals, maybe, for example, depending on what you need your robot to do. All right. Seymour Paper is in here somewhere. Papert. But just remember, he's the Mindstorms guy. So the last thing I'll talk about, I think, is Isaac Asimov and the Three Laws of Robotics. And I went on. I need to listen to this whole video and make sure I'm not repeating myself. So I'm a fan of Isaac Asimov. From like middle school, I read like 6th grade, I think. It's when I read the Foundation trilogy first. And you guys who don't know what I'm talking, you do know what I'm talking about. Knows what that series is. He's kind of like Lovecraft and other writers, I guess, in a way. I don't know. Is what's his face? He is a bit Stephen King, where you have all these different novels, books, stories, and you slowly build an actual like a whole world. Asimov sort of did this. So he had a bunch of books about robots. He had a few books about a galactic empire established by humanity, and then he had this Foundation series, which it's kind of a study, in a way, a psychological study of the fall of the Roman Empire, but in science fiction terms. So it was about the end of the galactic empire, a galactic empire, which turned out to be the one he connected it all. So it was the galactic empire that he had some of his stories set in before. It was about the study of the fall of that and how human beings might be able to foresee the fall of an empire or a civilization and try to minimize the impact of the fall and build a new civilization from the ashes, like shorten what he called the Dark Ages. Now, Dark Ages in real human history, that's a myth. There was no Dark Ages. It was some of the most educationally lively time, actually, during like the Holy Roman Empire with Charlemagne, and Alcuin was his name. Alcuin, I don't know how you pronounce it actually, but I think he was he English? An English scholar living in the Holy Roman Empire. But anyway, there was at the universities and monasteries and stuff, a lot of intellectual work was being done during the so-called Dark Ages. It's a myth, but saving of classical, ancient Greek and Roman knowledge was still well known. I mean, they knew the world was round, for example. That's a myth that everybody, the common peasant probably thought the world was flat, maybe, but the educated people knew the world was round ever since, what's his name, Aristophanes, right? The Greek several hundred years BC measured it using shadows. Big tangent. Okay, so he wrote these novels, and in these robotics novels, he had these robots, and there were some robots that were called humaniform. The original humaniform robot, his name was R. R stands for robot. R. Daniel Alival. I think these are Russian names. I think he was born in Russia, Asimov, and immigrated to America, I think, as a child. But he, R. Daniel Alival was kind of like Lieutenant Commander Data. Lieutenant Commander Data is very inspired by Asimov's robots. God, I hate repeating these things I just said in a different way. Data is an android. An android is a robot that looks like a human in some way or another, to some extent or another. So android comes from andros, which is the Greek word for man as opposed to woman. Anthropos is the Greek word for humanity. So anthropology comes from anthropos, right? Mankind, but both including male and female. Andros means a masculine man, like we're in Latin, versus femina in Latin. Homo is mankind, and humans. Homo is from Latin. But anyway, so a robot that looks like a human being to some extent or another is an android. So Data is not really humaniform because you can sort of tell that he's not a human being. But Arden and Alival, you had to like really scrutinize and know robot behavior to realize that he actually was a robot. But the robots in Asimov's universe are governed by these 3 laws of robotics. And I remember I told this story in the last take of this video that you didn't hear, that didn't record, but the first time I taught this class, I kind of scanned the comic book, but I didn't notice he talked about Asimov, and I recited them because I knew them. I haven't memorized. So the first law is a robot may not harm a human being or through inaction allow a human being to come to harm. The second law is that a robot has to obey the orders of human beings, but unless it would conflict with the first law. So they build on each other. And then the third is a robot must protect his own safety, existence, protect itself, unless that would violate either of the first two laws or both. So, for example, a human being could not order a robot to kill another human being. The robot would have to follow the order of a human, but if that order was to kill another human, that would violate the first law. So you couldn't have robots for hire. What's the dang name? I couldn't remember. Contract killer. What's another name for that when the spouse hires somebody to kill? You can't have the hitman. That's what you can't hire robots. You can't order robots to be hitmen because that would conflict with the first law. But any other order, including say, hey, robot, jump off that cliff. Jumping off a cliff would violate the third law, but not jumping off the cliff would violate the second law if a human being ordered a robot to do it. So like another more sensible scenario is that you order a robot to walk into a pit of lava to retrieve something that would save a human's life. Even if it didn't save the human's life, you could order it to walk into the pit of lava, right, or jump in front of a car or something if it had the strength to stop the car to save a baby. But again, if you take the baby out, the way the laws are constructed, it would still have to jump in front of the car if a human being ordered it to. But the third law just means that, hey, robot, don't willy-nilly walk off cliffs. That's like stupid, and it's like there's a lot of money invested in you. You need to protect yourself, right? So don't consciously walk off a cliff. That's ridiculous. Anyway. If you read the whole thing, Ardano Alival, there's another android. He's not humaniform. He's obviously a robot named Giscard. He accidentally gets telepathic powers through his programming. And over the eons, like 30,000 years, these two robots monitor humanity to kind of protect it. Part of the protection is not having robots. They kind of like made it to where because human beings would fall into laziness, stagnation if they had robots to rely on. So the Galactic Empire was settled by a contingent of humans who didn't have robots as a standard part of their society or whatever, and that was kind of subtly manipulated by the robots because it was good for humans in the first law to not have robots. It's hard to get like it. But anyway, over the eons they formulated a zeroth law, which is what Dr. Brown's referring to here, called the zeroth law is that a robot will not harm humanity or through inaction allow humanity to come to harm. So you could, for example, a robot that had those laws baked into its brain could kill a human being. Like the whole Hitler scenario is a baby, right? It could kill Hitler because it's good for humanity if it was a time-traveling robot with the zeroth law baked in. The problem was they didn't actually have these baked into their brain. The positronic brain, which is the concept you hear in Star Trek for Data, he has a positronic brain. That's Asimov's term for their brain. And the way the positronic brain worked, that baked into the very design of any positronic brain, were these three laws of robotics. So in the real world, I don't know if this is true, if he actually had this, but in his fantasy world, in science fiction world, you could not hack a robot, for example, to violate these rules because they're part of the fundamental design of a positronic brain, and it just wouldn't be a positronic brain anymore. The brain would just shut down. It wouldn't work. So that's obviously like probably in my understanding of computer programming, you could always like hack around that, but I don't know what a positronic brain is. It's a fantasy concept. So and these robots that came up with the Giscard, the android that came up with the zeroth law, shut down shortly afterwards because he couldn't be sure that his actions actually saved humanity after harming a human being. And if you read the books, the simplest robots, if you gave them two conflicting orders, the second law would make them just shut down because they wouldn't know what to do. So these laws were really firmly part of the programming. So right now we've got drones that will shoot bullets and fire flamethrowers, right? So these people seriously consider Asimov's laws as like a guideline to how we should try to make robots act. Again, I don't know if you can make it to where it's a positronic brain that's unhackable or not, but like even if not, these are considered fairly good guidelines. At least the first three. Leave the 0th out. That's getting too heady, I think. But all right, so that's Isaac Asimov and the 3 laws of robotics. So some sort of really ethical considerations about how we should design robots. And again, androids or a robot that looks like a human being. Anything else? Okay. I had to tell somebody it's recording. And they still don't care. I think that's the end of my lecture, though. I think I covered all the... There's Seymour Papert, by the way. Mindstorms. All right. So there's Papert. You need to know what a port is for the sensors. So like look at the Mindstorm stuff and make sure you know what all the parts of Lego Mindstorms are, and know what a port is. It's where the sensors hook up. That's about it, really. So I just wanted to like point out some of the main things you need to see, and then give you some of my share some stuff that I like about robots. I could go on for days about robots. I'm just trying to leave this video under 30 minutes though. So if you have any questions, or maybe I should put up a discussion board where you talk about robots, I might do that actually. Look for that. I'm not sure if I will, but probably at this point. So there's a lot in Battlestar Galactica, Terminator, Doctor Who to some extent. I mean, they're not really Cybermen or cybernetic organisms, and Daleks are too in a way. So, but there's certainly a lot to talk about. But yeah, the materials you have are good for this week, so just make sure you read through them. At least the comic book. Come on, it's easy and it's usually enjoyable. So make sure you read through that at the very least. But I recommend looking at all the stuff and looking at the supplemental stuff I added. You don't have to read Craig Reynolds' paper. It's a very long, probably. I haven't read it. I've read parts of it. So I've read more like articles he's written, not the paper itself. So, but it wouldn't be bad if you read it, but you don't need to for the class. Okay, talk to you later.